In the last video, we built this awesome gRPC server with which we can extract and expose information out of an inertial sensor. With it, we can extreme data like angular velocities and acceleration. And today, we're going to learn how to make sense of that data. And we're also going to learn how to apply the simplest form of sensor fusion. Shall we do a quick recap? In the last video, I've shown you the entire process of how to, all the way down to the sensor module, how to get the information out of the sensor and make it available via gRPC service. Why? So that any client that has any interest in the data can literally just subscribe to that service, and the data is going to be streamed out of the sensor in real time. And that is precisely what we're going to do today. Today, we'll be on the client side. We're going to consume that information. We're going to subscribe to that service. We're going to stream that data to us so that we can do our best possible estimates of the roll angle and the pitch angle. So we're going to be estimating rotations. And to assist us, I've created another software, another gRPC server that allows clients to push data and render information in real time. This is how it looks like. So this is what I call the remote plotter. With it, we can visualize in real time any signal. In that case, I am plotting, and I can even zoom in and out. I can make it visualize only the same amplitudes. So right now I'm just pushing accelerometer information in blue and a fused information that we're going to see how to do later on of that same measurement. One thing that I really am proud of is that the entire process of configuring your signals and your access is fully done via service. So this is the gRPC server. It is rendering a window by default, and this is a client. And with the client, we can configure, hey, I have 3 signals, I have 2 axes, this is the signals that I'm be measuring, and this is what I expect the colors to be. So the entire configuration is also done remotely via the RPC. If I disable the inertial sensor, so I stop the publishing side, I just get the plots with nothing. So it's very flexible. I'm really proud of it. Maybe you like it, maybe you want to use it yourself. I'll leave that to you. And the link in the description. Okay, so the whole infrastructure is ready. We have a sensor publishing information, we have a plotter listening for connections and waiting for signals to be rendered. Our job today is to work in the middle, intercepting the sensor information, processing it, and publishing them to the remote plotter so that we can visualize. So that's where we're going to focus today, on this middleman. Let's start with a bit of theory. Accelerometers, as the name suggests, measure acceleration. This acceleration may be because of either gravity or linear motion. So if I don't do anything with the accelerometer, as it is right now, just stand still, what it is gonna feel is solely the influence of gravity. And there we can see on the acceleration axis Z, it has amplitude 1. If I change the angle like this, the gravity was shifted to another axis. And if I do like this, all right, so what you saw here is the influence of gravity under the accelerometer measurements. However, the accelerometer also measures linear accelerations like this. This is not gravity. If you look at the axis Y, this is me disturbing the y-axis, and this is me disturbing the x-axis, and this is me disturbing the z-axis. Why is this important? Because if we want to make estimates of rotation angles, we need to make an assumption. We have to assume that there is no influence of linear motion under my measurement, which is a strong assumption and is hardly true. But that's an assumption we have to make sensible calculations. And because we're making that assumption, this implies that the formers that we're going to use will suffer from any acceleration that is not because of gravity. And that's just the way it is. We have simpler equations, but we have strong assumptions, and if the assumptions are not correct, we will suffer. The other thing that I wanted to point out is you might be wondering, why are you only interested in the roll angle and the pitch angle? The reason is, with accelerations, we can not detect yaw motion. So the orientation like this, it is not detectable. Why? Because the gravity is vector that is parallel to that axis of rotation, meaning that the influence of gravity cannot help us in detecting that motion. So keep that in mind. Okay, let's continue with this assumption. what does the formula look like? It looks like this. I'm not gonna go into too much detail. This is standard Euler angle matrix notation. This is, going very briefly, this is how you get equations that will yield the angles based on accelerometer measurements. Starting from the left, this is the measurements that we get directly from the acceleration, AX, AY, and AZ. This is what actually the sensor outputs in its registers. And to the right side is the equation that has our assumption inside that all the influence that the sensor detects is due to gravity. And that influence accepts two rotations, and neither of those rotations involve the yaw angle, so the angle around the gravity vector. And this is how it looks like. So first we do a rotation around Y, then we do a rotation around X. This is a standard rotation matrix equations, and here we have gravity vector. If you do this math, you get this final formula, and if you think a little bit more, this is the standard angle that you obtain. So you can detect roll and pitch purely based on accelerometer measurements. I think that's really cool that you can get from those equations, which encodes a bit of the reality, into measurements, and then you can do your estimates. I think that's really cool. Now let's try to apply these equations directly with the measurements that we're getting from accelerometers. How does that look like? Let me just configure which axis I want to show on the right side with this nice little gRPC server that allows us to plot whatever we want. Okay, so I want to add a new axis called estimates. I'm gonna keep this accelerometer measurements, the raw ones. I'm gonna keep it. I'm gonna add a new axis, and then I'm gonna add two new signals. The first signal is the pitch, the roll, and then the pitch, and they're gonna get their names. If I do like this is just for configuration. Looks like it worked. Let's have a look at the main loop. This is the main loop from this little guy that we saw before. So we are right here in the middle, put this away. And this is every time we get a sensor measurement from the gRPC server that is hosting the sensor measurements. Every time we get a sample called sample, I do some filtering on the delta t, and here we see the equations that I just showed. Add them to some square roots, and then we convert to degrees, and then this is the calculation. And here with my plot server, this is a batch of points that we could render at the same time, and this is the raw signals, and this is the ones that we just calculated, and these are going to be discarded for now, but we will have a look at them later on. So if I just run it, and I'm also gonna render a little board here, running, make it small. Here we go, and I'm gonna make this like this. All right, so this is the output of the equation that we just discovered. Roll angle is the angle around that axis, because this is X, this is X, this is the roll angle, this is the pitch angle. Let's try to see what happens with the roll angle. See, how cool is that? We see, and this is in degrees, so I go all the way to 90. We get a pretty good estimate on that angle. Well, pretty good is a strong definition, because to me it seems very noisy, but okay. Then if I do like this, and then we go with the pitch, same thing. See how the roll is feeling the influence of the pitch. Not to think too much about it, but apparently, yes, apparently this equation does work up to 90 degrees. Perfect. And of course, all the way to the side. This looks like this is 90. Yeah, 85. A little bit noisy here. Yeah, sounds like the equations are okay-ish. Looks a lot noisy. Yeah, because the fluctuations vary in 10 degrees. So yeah, I think it could do better. But okay, the equation works. It is, yeah, it's a bit noisy, but it works. What about the gyroscopes? Glad you asked. Gyroscopes measure angular velocities, meaning that rotations around that axis, exactly the same rotations we saw before, they are actually measuring that velocity. Rotations around that axis are being measured, and rotations around that axis are being measured. All right, looking at the gyroscope equations, it is way more simple than the accelerometers. All we need to know is the actual thing that it measures. So the gyroscopes measure angular velocity. So around x-axis, so around this axis, the rotation, the actual measurement of the gyroscope is what we need to know. Then we multiply that by the delta time, that is the sampling time, how much time in between samples. This is basically velocity times speed equals space. In angular terms, angular velocity times time equals angle. And this is the case for all those three angles, including the yaw angle that the accelerometer cannot measure. And that's it. All you have to do is exactly follow this equation. And if you build up, so if you keep accumulating this velocities times time, you build up to the angle that you're trying to estimate. All right, so let's have a look at how the signals looks like. So first, let me just check the configuration. So here I'm just configuring my axis to accept those signals, same axis ID, everything looking good. Then we go to the main loop. In the main loop, we do a small filtering that happens in the first sample. What matters is that we are computing the delta t, how much time it has passed since we last got a sample. Then we multiply that by the sample measurement. So this is the actual measurement of the gyroscope, and then we accumulate that over in the same variable, and we make sure that's converted to degrees. All right, and here I'm just plotting the whole batch of points that is being streamed to the remote plotter. Let's run it. And this is what we get. At the top, you see the raw gyroscope measurements. They seem noisy, to say the least. This begin, and notice the following. If I don't do anything, this gyroscope is just standing still. Already, because of that noisy output of the raw measurements, already I get some kind of bias. It's adding up to something that I'm not expecting. But let's ignore that for now. Let's show what this equation will yield when I do the rotation. That's the pitch. We are rotating around the y-axis, looking nice. So if I ignore the fact that this is biased, it is quite smooth, way more smoother than the accelerometer measure. And there's nothing wrong with rolling a little bit too much. See? How about the roll? Roll is around the x-axis, looking very smooth as well. And if we zoom in, you can see that it's very smooth. There's almost nothing bad about it, except the bias. Again, if I stand still, look at what happened. The bias accumulates over time. That is bad enough. I cannot trust that sensor alone, which is a pity. And that's where the beauty of the sensor fusion lies. We have biased, smooth measurements, and we have rough, precise measurements of the same thing. We're trying to measure the angles. How do I combine those? How do I fuse those in a sensible way that I don't lose information? I really make the best of both worlds. Sensor fusion. The simplest form of sensor fusion is something called complementary filter, where you have a biased, smooth measurements, exactly as we do, and we have a rough, correct measurement of something. So the accelerometer is rough, but it does measure its average is exactly where it should be. So it's rough around the correct value. If you have this pattern, we can use something called complementary filter. Complementary filter is extremely simple. Let's not spend too much time reading anything at this moment. What is important here is that this is kind of a combination of low pass, high pass filter, in which you have a single variable of parameter called alpha, and that alpha will balance which is the sensor that you're favoring the most. Is it the accelerometer or is it the gyroscope? With a simple equation, you are fully capable of implementing a fused measurement. All right, let's see how that looks in practice. So here I am reconfiguring the axis. We're gonna print the gyroscope measurements and the fuse measurements. I'm not gonna print the accelerometer measurements because it's gonna be ugly, but trust me, we've seen it before. It's rough, it's like this. All right, going to the main loop, here we are again. We start our fuse measurement as 0, and look at how simple that equation is. We have an alpha multiplying the gyroscope part, and we have 1 minus alpha multiplying the accelerometer the noisy part. That's as simple as that. The reason it converges to the accelerometer measurement is because this alpha is never 1. If this were 1, this term would be 0 and you would converge to the gyroscope alone. But as long as this is less than 1, if alpha is less than 1, your measurements will always converge to the accelerometer, right? There's a few mathematics reasons for that. What matters is that there is a convergence towards the accelerometer measurement, and that is what guarantees that this fused information will not get the bias out of the measurement. Let's see how it works. So here in blue and blue cyan, we see the fused pitch and row, and already we notice that it does not deviate from 0. The gyroscope is going crazy already, bias, and not the fused one. And if I go to rotations, the bias is completely off. But if I turn, let me show you the rotation. If I turn almost 90 degrees, the fused information is almost 9 degrees and the biased one is like completely off. So here we see the fused roll. How about the pitch? Same thing. We converge to whatever it should be. We saw a dip here because there is some non-linearity in the equation, but we don't have to think too much about it. But we see the measurement is very smooth. Just like that, we have applied a fusion of sensors. Let me remove 2 gyroscopes. They're messing a little bit. Now we only have the fused information. How smooth it is. And let me now compare to the accelerometer actually, which is always centered around the correct information. See, it converges to the same value, but it's way more smoother. And that goes for both angles. If I move this, we see here fused pitch looking much nicer. And that, my friends, is sensor fusion. So now you know how to implement a complementary filter, which is I would say it solves 90% of the problems out there, but for the 10% that you need extra precision, accounting for multiple variables, multiple parameters, many more states, we're gonna have to use something called Kalman filtering. Thank you very much for watching this video. I do hope you have enjoyed it. I think that's a fascinating topic, incredible topic, and we can do so much with it. Stay tuned for the next one.